This is part 2 of the lecture on power. We're going to do 2 basic examples here to give you an idea as to why we bother to define power. We define power because it neatly illustrates the problems that we encounter when doing engineering. In the second example, I'll also give you an idea as to exactly what is meant by a horsepower. Okay, go ahead and copy down the first of these 2 problems into your notes as I read it here. Okay, a machine, that's going to be me in this case, pulls a 1 kilogram object horizontally. So here's a 1 kilogram object. And I pull the object across the surface with a force of 10 newtons for 5 minutes. 10 newtons is just a couple of pounds of force. So I basically just do this. We're going to ignore friction here with the table. However, I don't pull on the object for just a couple of moments, as you saw me do here. Instead, I'm going to pull on the object for 5 minutes. The object is initially at rest. Okay, in part A and B of the problem, we're going to do a little bit of F equals ma to find the acceleration. Then we're also going to calculate out some basic kinematics quantities. We're going to find the final speed of the object and the distance traveled. So let's do that basic portion of the example here first. Okay, so here's our situation. We have this horizontal surface and it's frictionless. So let me go ahead and note that here. Okay, here's our object of mass m equals 1 kilogram. And it's initially at rest. The initial speed v naught is equal to 0. Okay, and then I come along and I exert a force like so horizontally. I'm going to call it F push to give it a name, and that's given to us as 10 newtons. And then I pull the object or push the object over to here. It will have a final speed v, and it's also going to undergo right here with displacement delta r. So we're going to calculate the displacement, the distance traveled, and the speed v in parts A and B of the problem. Okay, in order to do so, however, we need to know what the object's acceleration a is to the right-hand side. So let's just do a little bit of F equals ma. So if we look at the forces that are exerted upon the object and we ignore friction when we do this, there are only 3 forces acting. We have, first of all, vertically, the normal force and the object's weight canceling each other out. And then horizontally, we have my F push to the right-hand side in the same direction as the acceleration. So if I add up the forces horizontally, we only have 1 force, and that's F push. So then therefore, F push is equal to the net force. F push is equal to ma. So it's 10 newtons divided by 1 kilogram for the mass. This then gives us the acceleration a as 10 meters per second squared. So 10 meters per second squared is a little bit more than a g. So it basically looks then something like this. Initially, when I push the object in that direction, I'm doing so in acceleration of about 10 meters per second squared. But now we do this for 5 minutes. 5 minutes is 5 times 60 or 300 seconds. Okay, and now let's go ahead and take a look at part A of the problem. We're going to find the object's final speed. So in part A, we're going to use this kinematics equation that we saw in the earlier unit on kinematics for constant acceleration. And then in this case, the initial velocity v naught is equal to 0. So then therefore, the final velocity is just a times t. So this is 10 meters per second squared multiplied by 300 seconds. This then gives us 3,000 meters per second. 3,000 meters per second is 3 kilometers per second. So if I, for example, do this, exert a force of a couple of pounds, say in that direction, but I do it for a full 5 minutes, then the object reaches a speed of 3 kilometers per second. Why can't I do this? Well, that will be illustrated when we do the power calculations later on in the problem. Okay, let's calculate the distance traveled. So in order to calculate the distance traveled here in part B, we're going to use this one-dimensional kinematics equation for constant acceleration. So we've seen this before. And in this case, once again, the object starts from rest. The initial speed here, v naught, is equal to 0. So then therefore, the distance traveled is going to be 1/2 at squared. So let's now just go ahead and plug in these numbers. So I have 1/2 and then times the acceleration of 10 and then times 300 squared. So when I plug everything in, this ends up being 450,000 meters. Let me write this correctly. There we go. 450,000 meters, which is 450 kilometers. So if I do this like so, and I do it for 5 minutes, the object ends up out in the Mojave Desert somewhere, a few hundred miles away, for example, and it's doing so at a speed of 3 kilometers per second. Once again, why can't I do this? This has to do with the power calculations now for the remainder of the problem. Let me go ahead and move it here on my screen and I'll read it to you. Okay, so now in part C of the problem, we're going to calculate the average power output of the machine. So the power output of the machine is basically the work that I do per time when doing this in the example. Okay, let me move to the lower board for that purpose. Okay, so we're going to go ahead and write this now as P bar for average and then machine. So this is equal to the work done by F push in this problem. That's the force that's exerted by the machine, and then we divide it by time. So then therefore, because F push and a displacement point in the same direction, then we just have force times distance in the numerator. So force times distance, and then we divide by time, and then we'll end up here with a certain amount of watts. Let's go ahead and calculate that. All right, so let's see. We've got F push, which is 10 times 450,000 meters. Let me make sure I punch in all the zeros there correctly. And then divide by the time of 300 seconds. This ends up being 15,000 watts. Okay, notice how large this number is. Basically what this number means is the following. Over this broad time interval of 300 seconds, on the average, the machine has to deliver to the object 15,000 joules of energy per second. That's difficult to do for a couple of reasons. Number one has to do with what is called the energy density of your fuel. Think of energy density as how much bang you have for your buck. If you're talking about, say, gasoline, there's only so many amounts of joules of energy present in 1 per unit volume of the gasoline itself. In other words, how many joules you have per meter cubed of gasoline. This is referred to as energy density. So the lower that number, the less quickly you can deliver that energy to the object. And then when you do deliver the energy to the object, you have to convert that energy from chemical potential energy, for example, into the kinetic energy of the object itself. You run up against constraints in doing so with respect to the actual construction of your machine. So the reason why I can't take this object and accelerate it up to 3 kilometers per second is because, number one, the energy density associated with the chemical potential energy of my muscles is small, and then the structure of my body literally prevents me from doing this amount of work that quickly upon the object. So then therefore this power output calculation, it illustrates the problems that we run up against when actually doing engineering. You can only deliver the energy to the object so quickly, and in part you're constrained by the energy density of your fuel. The problem is also worse, by the way, when you take friction into account, because when you take friction into account, you generate heat, and you have to get rid of that heat as quickly as possible. If you don't get rid of that heat, then the object is going to melt, or your engine is going to melt, and obviously you don't want to have that happen. So if you do a power calculation associated with friction, then you're illustrating the amount of heat that you have to get rid of per second. We're skipping that, however, in this example. The problem compounds itself. It gets worse and worse the faster you go. That's basically part D of the problem. Okay, in part D of the problem, we're calculating the instantaneous power output of the machine when the object is moving at a speed of 3,000 meters per second. So this is going to be equal to F push, and then multiplied by our speed V of 3,000 meters per second. 3,000 meters per second times 10 newtons is 30,000 watts. So in order to keep the object moving at that speed, the engine has to deliver to the object 30,000 joules of energy per second. This illustrates why very quickly when you stamp down on the accelerator of a car, the car reaches its top speed pretty quickly. Once again, the constraints that you are running up against is basically delivering that amount of energy per second to the object. It is very difficult to deliver this amount of energy per second to the object in order to keep it moving at this enormous speed. So power, the reason why we define it is because it very nicely illustrates the problems that we run up against when actually doing engineering. Okay, now for my second example, this is for those of you that may be into cars. Let me give you an idea as to exactly what is meant by a horsepower. So let me go ahead and erase this problem. We've completed this example, and then we'll move on to the second example in just a moment. All right, so let's get rid of all of this. Okay, then let me move my file. Okay, and then let me go ahead and read the next example to you. Okay, horse pulls a cart horizontally while exerting a force of 40 pounds. Notice the English units here, and 40 pounds is considered to be a light load. Okay, the horse pulls the cart at a constant speed of 9 miles per hour. What is the instantaneous power output of the horse? So because the cart is moving at a constant speed, the average value and the instantaneous value are the same thing. Okay, now here's what the example looks like. What I'm going to draw is a force diagram here for the forces that are exerted upon the cart. So upon the cart, we have first of all the normal force upwards and the cart's weight canceling each other out. And then we have the force that's exerted by the horse. I'll call that F pull. It's equal to 40 pounds. Opposing the motion is an equal amount of friction. And the reason why that frictional force equals F pull, it's because the acceleration is equal to 0. And then the horse is pulling the cart in this direction with a speed of 9 miles per hour. Okay, what I need to do first here in order to calculate the instantaneous power output of the horse is I need to convert the miles per hour into the base units, which are feet per second. So first of all, hours. 1 hour is equal to 60 times 60 or 3,600 seconds. So I'm going to convert hours to seconds by doing that. And then there are 5,280 feet in a mile. So let's now go ahead and multiply by 5,280 feet per mile. And then miles cancels here and here, and we'll end up with a speed in terms of feet per second. So let's go ahead and convert it. 9 miles per hour, by the way, is like a steady jog for a human being. Okay, so 9 times 5,280 and then divide by 3,600 after we do the math here. This ends up being 13.2 feet per second. Okay, and then the instantaneous power output of the horse, let me do this on the lower board. I'm going to call this P horse, is as follows. It's first of all the force to the right-hand side, F push of 40 pounds, and then multiplied by the speed here of 13.2 feet per second. So if I just multiply by 40 pounds, this comes out to be 528 foot-pounds per second. Those are the English units of power. But now let's convert this into a horsepower. I'm going to multiply by 1 horsepower per 550 foot-pounds per second. This is the conversion factor between the two, and no, you don't need to know that conversion factor off the top of your head. Okay, let's cancel out the foot-pounds per second, and then we'll end up with the power in terms of horsepower. So basically divide by 550. And this is very nearly equal to 1. It's 0.96 horsepower. So 1 horsepower is nicely illustrating what a beast of burden can do in an agricultural situation. A horse pulling a light load of 40 pounds, and it's doing so at a speed that's equivalent to a good jog for a human being. So for those of you that know anything at all about sports cars, for example, usually the maximum power output of high-end sports cars is in the neighborhood of just over 1,000 horsepower or so. So imagine 1,000 of these, for example, as describing more or less the capability of the internal combustion engine. Okay, that concludes this brief look at power.